Ever wonder how your computer can find one file out of thousands in just a blink? Or how your social media feed knows exactly who's connected to who? Well, the secret isn't always a simple, straight line. Sometimes, to make sense of all this data, you've got to let it branch out. We're all pretty used to thinking about data like this on the left. Linear data. It's like a list or a train on a track. You start at the beginning and you just follow the path to the next stop and the next. But what if one stop could connect to a bunch of other stops all at once? That's hierarchical data. And the absolute superstar of that world is a structure that looks just like this diagram, a tree.
So here's our game plan. First, we're going to go beyond that straight line. Then we'll get into a super important idea called the two-child rule. After that, we'll learn how to actually walk through these branches, we'll meet the ultimate data organizer, and finally, we'll tie it all together to see why trees are just so critical to our digital lives.
All right, let's dive right in. Part 1. Beyond the straight line. We already know that not everything fits neatly into a single file line. So what actually happens when we let our data branch out?
Okay, here's the official breakdown. A tree is made of nodes. You can think of those as the little bubbles holding our information, and edges, which are the lines connecting them. Now, the key here, the thing that changes everything, is that a single node can have multiple next elements. It's not just a chain, it's a family tree where one parent can have many children.
And believe me, this isn't just some abstract theory. It is the invisible architecture holding up so much of what we do. The file system on your computer? That's a tree. A company's org chart? Yep, that's a tree too. They're used in databases to find information at lightning speed, and they even help route internet traffic so you can watch this right now. They are literally everywhere. So a tree node can have a whole bunch of children. But things get really interesting and way more powerful when we add one simple rule. So let's talk about the two-child rule and the most famous tree of all, the binary tree. So a binary tree is exactly what it sounds like. It's a tree with a very strict policy. Every parent node can have at most 2 children. And we're very specific, we call them the left child and the right child. Now, this might sound like a limitation, right? But it's actually a brilliant move that opens the door to incredible speed and efficiency. And here's why that's so important. It all comes down to solving a classic problem in computer science. Just look at this showdown. You've got arrays. They're super fast for grabbing something if you know its exact position. But adding or removing an item, it's a total pain because you have to shift everything else around. Then you've got linked lists. They're the opposite. It's easy to add or remove links, but finding something takes forever because you have to go one by one. And then you have trees. They give you the best of both worlds, fast access and fast changes. That simple two-child rule makes everything easier because you only ever have to think about left or right. The logic for finding things, for adding things, for deleting things, it all becomes way simpler and faster. This one little rule is the foundation for one of the most powerful data structures in existence, the binary search tree. Okay, so we've got this awesome branching structure. But how do you actually visit every single node in an organized way? I mean, it's not a straight line, so you can't just start at the beginning. You need a strategy, and that strategy is called traversal.
There are really 2 main ways to think about this. You have breadth first search, or BFS. I like to call this the level-by-level explorer. It checks out all the neighbors on one level before moving down to the next. It's perfect for finding the shortest path, kind of like how your GPS finds the quickest route. Then you have depth first search, or DFS, the branch-by-branch explorer. This one dives all the way down one single branch to the very end before it backs up and tries another. For our purposes, we're going to zoom in on depth first search because it has a few really important patterns that come up all the time. First up, we have pre-order traversal. The pattern is simple. Check out the root node first, then explore the entire left side of the tree, and only then do you explore the entire right side. Because you handle the parent before its kids, this is the perfect method if you ever need to create an exact copy of a tree. Next is in-order traversal. Notice the difference? Here, you explore the whole left side first. Then you visit the root, and finally, you explore the whole right side. The root gets visited in between its children. Now, file this one away because this pattern is absolute magic when your data needs to be sorted. And that brings us perfectly to our 4th section, the ultimate organizer. We're going to take that binary tree we talked about, add one more simple rule, and create something incredibly powerful. the binary search tree, or BST for short.
This right here, this is the golden rule of the BST. For any node you pick in the tree, everything in its left branch is smaller, and everything in its right branch is bigger. This one single property transforms the tree from just a storage container into a highly intelligent searching machine.
So what does that rule get us? Incredible efficiency. The time it takes to find something is related to the tree's height, which we write as O of H. Now, in plain English, that means you don't have to check every item. Get this. For a reasonably balanced tree with 1,000,000 items, you can find the exact one you're looking for in about 20 steps. Not 1,000,000 steps, 20. That's just mind-blowing.
All right, so let's put it into practice. Take a look at this binary search tree. How would you find the number 35? Well, you always start at the top, at the root, and you ask one simple question. Is my target higher or lower? 35 is higher than the root, so we can completely ignore the entire left half of the tree. We just go right. At the next node, we ask again, is 35 higher or lower? This time it's lower, so we go left. And boom, there it is. In just 2 steps, we zeroed in on our number by throwing away huge chunks of data with every single decision. It's so elegant. So let's bring this all home. In our final section, we're going to answer that big so what question. Why does any of this really matter?
You know, this quote really just says it all, doesn't it? Trees solve that fundamental dilemma we talked about. You no longer have to pick, do I want fast access or do I want fast updates? With trees, you get both. It's the best of all worlds.
So here's what I want you to walk away with. First, trees are for hierarchical data, not straight lines. Second, binary trees give us a simple but really efficient structure with that 2-child rule. Third, binary search trees take that and add a sorting rule that makes finding data unbelievably fast. And the big takeaway? They offer that perfect, powerful blend of speed for both finding and changing your information. So while they might feel a little abstract, trees are truly the invisible architects of our digital lives. The next time you search for a file or scroll through your feed or even use a map, just remember the elegant branching logic that's working tirelessly behind the scenes. And it makes you wonder, right? What other hidden trees are shaping your world right now?